All right, welcome to your first virtual lesson. This is on section 5.2. By now you should have already completed your guided reading notes. Please have those out and in front of you because you're going to need to refer to it as we go through these examples, because that's really all I'm going to be doing is examples. So let's start with something relatively simple. Imagine flipping a fair coin 3 times. The fair part means that the outcomes are going to be equally likely. It's not a weighted coin. So both heads and tails are going to be equally likely. Describe the probability model for this chance process and use it to find the probability of getting at least one head in 3 flips. So we're going to be doing 3 things for this example. One of them is I'm going to use a diagram to represent the situation, flipping a fair coin 3 times. Then I'm going to use that diagram to make the probability model, and then I'm going to find the probability of this thing getting at least one head in 3 flips. So I'm going to start by using a tree diagram to represent what's going on here. And many of you guys have probably already seen this before. In a tree diagram, each branch represents a different outcome. So here I'm going to start with my coin, and there are 2 possible, and in this case, equally likely outcomes, which is heads and tails. So this branch represents heads, and this branch represents tails. On the second flip, I also have 2 possible outcomes, which means I now have a total of 4 possible outcomes. So this branch represents getting heads and then heads, heads and then tails, tails and then heads, tails and then tails. And of course on the third flip there are also going to be 2 possible outcomes, which means I end up with a total of 8 possible outcomes. So that top represents getting heads and then heads and then heads, whereas this branch down here represents getting tails and then heads and then tails. So I'm going to go ahead and summarize what are the different outcomes we could get, which are going to be getting heads, 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 tails, tails, heads, tails, etc. Now in this case, because each of these outcomes is equally likely, each of these probabilities is going to be exactly the same. In fact, each of them is going to be 1 out of 8, because there were 8 possible outcomes, and each of them is equally likely. So hopefully you're starting to see some of those probability properties that you had to write down in your guided reading notes already. Now, the second part of this is the probability model. But the only thing I'm really interested in is not really so much the individual outcomes as I am the number of heads. So how many heads could I get if I flipped a coin 3 times? Well, I could get heads 0 times, 1 time, 2 times, or 3 times. So the probability of getting 0 heads is pretty easy, because that would mean I got tails and then tails and then tails. This is the only outcome that means 0 heads. Similarly, this top branch is the only outcome that represents getting 3 heads. So for the 1 and the 2, I have to actually go through and count. So which of these branches represents getting exactly 1 head? Well, this one has 1 head, this one has 1 head, and this bottom one here has 1 head. So those 3 branches represent getting exactly 1 head out of those 3 flips. We also have this branch here that has 2 heads, this branch that has 2 heads, and this branch that has 2 heads. So there are 3 branches that have exactly 2 heads out of 3 flips. So my probability model is going to look like this. Remember, a probability model includes all of your possible outcomes as well as the probability of each of those outcomes. Both the 0 and the 3 had exactly 1 out of the 8 branches, which is why the probabilities are 1/8. And the 1 and the 2 had 3 out of the 8 branches, which is why both of those probabilities are 3 out of 8. So that's the second part, which is I'm going to make a probability model. The last thing is figure out what's the probability of getting at least 1 head. So at least 1 head means 1 or more. So that means I could get 1 head or 2 heads or 3 heads. So one way of getting it would be to add those up. Say, all right, well, 1 or more means everything here and to the right, so it would be 3 out of 8 plus 3 out of 8 plus 1 out of 8, which is a total of 7 out of 8. The other way of approaching this is to say, wait a second, all of these branches are included here except for this very last one. That's the one that has no heads in it at all. So the other way to do it is to say, okay, then this had a probability of 1/8. So everything else is what I want to include in the probability of at least 1. So you could figure it out by doing 1 minus that 1. So the probability of at least one head is going to be 7/8. Two different ways to think about it, which is add up the different outcomes that give you that, and for a total of 7/8. And the other is going to be using the complement rule, which you guys already have notes about. So 1 minus no heads gives you 7/8 as well. So let's review some of those probability rules that you guys wrote down in your guided reading notes by talking about probability models. So here, this is the actual score distribution for students who took the 2010 AP Stat exam. Actually, no, that's not true. This is not the actual one. This is from a sample. So we took a sample of students and recorded their score that they received on the 2010 AP Stat exam and recorded their scores. So again, this is supposed to be a probability model, so this should include all of the possible outcomes as well as the probability of each of those outcomes. To show this is a legitimate probability model, this is going to be those first two properties you guys had for probability. The first one is that all probabilities should be a number between 0 and 1, which all of these numbers are. The second part of it is going to be all of the possibilities, all of the probabilities together have to total to 1 or 100%. Because, I mean, one of these outcomes has to happen. So to show that something's a legitimate probability model, you need to check both of those things. So again, all of these numbers are between 0 and 1. And if I add up all of them, I get a total of 1. So it is a legitimate probability model. Part B, find the probability that the chosen student scored 3 or better. So 3 or better means 3 or more because 5 is the best score and 1 is the worst score. So the way most people would approach this is they're going to say, all right, and that's the probability of getting a 3 or a 4 or a 5. So to find the probability of 3 or better, I'm just going to add together these three numbers. And if that's what you think, you're exactly correct. The total probability is going to be a little bit over 58%. So a little over 58% is the probability of randomly selecting a student that scored 3 or better. Finally, find the probability the chosen student didn't get a 1. Two ways to think about this. One of them is to say, okay, the people who didn't get a 1, that would be the people who got 2s, 3s, 4s, and 5s. So I can find that by adding together these numbers, which is correct. You can find the probability of not getting a 1 by adding together the probabilities of getting a 2, 3, 4, and a 5. So I get a total of 0.767. The other way of doing it again is to use the complement rule. So that would be didn't get a 1 is everybody except these people right here. So the other way I could do it is to do 1 minus this probability, and I would still get the exact same answer, which is 0.767. Alrighty, so that's it for basic probability. Let's talk a little bit about Venn diagrams and two-way tables. Now, two-way tables and Venn diagrams are really, really helpful when we're dealing with a specific situation, which is when you're talking about probabilities of 2 or more events. Really just 2. Beyond 2 events, you're probably going to be better off using a tree diagram. But let's see an example. So, students in a stat class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on 2 variables, which are displayed below. These are 2 categorical variables. One of them is gender, which is male or female, and one of them is whether or not they have their ears pierced. So the first thing I should do is I'm going to define some variables here just so I can stop writing out male, female, ears pierced, not pierced. So I'm going to let A represent the male, the event that the person is male, and B is going to represent that they have their ears pierced. So if A represents male, then female is going to be not A, or the complement of A. Similarly, if B represents having their ears pierced, B complement, not B, is going to be their ears are not pierced. The last thing is, it's going to be a lot easier to find probabilities using this if I go ahead and find the row and total columns. So let's go ahead and do that. So there are a total of 90 male students, 88 female students, 103 students with their ears pierced, and 75 students without their ears pierced, for a total of 178 students. All right, so here are some questions. Find the probabilities that a student has pierced ears. So it's important to remember what's going on the top and what's going on the bottom. On the top is going to be those that fit this particular condition, those that have their ears pierced. In this case, I have a total of 103 people who have their ears pierced. out of the total, which is 178. So we're going to get 103 over 178. It is really important that you write this fraction down on your paper because it's considered showing work. Even if your final answer is going to be a decimal, this is considered showing work. Also, you do not have to reduce your fractions. The only exception would be if you're doing a multiple choice question and the answers are reduced fractions for some reason. This one doesn't actually reduce, but it's good to know you don't have to reduce fractions in this class. Is a male with pierced ears? So that means that they are male and they have their ears pierced. So the people that are in that category are here. These are people who are male and have their ears pierced, which is 19 out of my total, which is 178. So my probability is going to be 19 out of 178. And finally, is male or has pierced ears. Now the word or is one that trips up some people. So to say the probability that someone is male or has pierced ears means that they could be male or have pierced ears or both. It's not just one or the other. If you've studied logic or computer science, you might have learned about what we call an exclusive or. That's not what we use in probability and statistics. So to qualify to be in this group, you could be male or have pierced ears or both. There's a few ways to think about this. So these are people who are male, and here are people who have their ears pierced. Now, for a lot of people, your first thing you want to do is to do this 90 plus this 103 and put it over 178, which is not right, but you're almost right. Let's talk about a couple other ways to figure this out first. So male or has pierced ears represents these people here. These people. So you could be male or pierced ears or both. So one way to figure this out would be to, okay, add up those three regions. So what are those three regions? 19 plus the 71 plus the 84 out of my total, which is 178. That's one way to think about it. Another way to think about it is to say, hey, this is everybody except these four people here who are female and don't have their ears pierced. So you could figure it out using the complement rule. You could say, all right, it's everybody in this group except for those four, which would be 178 minus those 4 over 178. And the last way, which some of you guys might have thought to do, is to do the 90 plus the 103. But the problem with that is the 90 is 19 plus 71. And the 103 is the 19 plus the 84. So if we just do the 90 plus the 103, we're double counting these 19 people. So the solution to that is to remember, if you're going to use that strategy, you're going to do the 90 plus the 103, subtract out the 19 people that got double counted out of the 178. Any way you do it, you still get the same answer. You do, however, need to understand and be able to use all three of those methods to answer the question. Alrighty, so one more for this part of the video. What's the relationship between educational achievement and home ownership? So we have two different variables, what your level of education and whether or not you own a home. And we want to put this in a two-way table. So this is the way I decided to do my table. It does not matter if you decide to put your homeowners on top or on the side, or a high school grad on the top or on the side. And then we're going to use the information they gave us. So we know we have 500 people total, so that's going to be my total. The 340 is the total who are homeowners. The 310 are the total who are high school grads. And the 221 are people who are both homeowners and high school grads. Go ahead and pause the video and see if you can fill in those other cells. If you did, you should have gotten these numbers. The probability the member is a high school graduate, 310 out of 500. High school graduate and owns a home, 221 out of 500. Is a high school graduate or owns a home is going to be 429 out of 500. Now, again, there are a few ways you could have gotten this. You could have done the three regions that are included. You could have done everything minus the one region that's not included. Or you could have added the 340 and the 310 and subtracted out the people who got double counted. And that is actually why this is so powerful, because if you did the 340 plus the 310 minus the 221 that got double counted, you actually didn't even need to make this table to begin with to answer any of these questions, because you could have just said 340 plus 310 minus those that are both, and that would give you the probability that they're a high school graduate or they own a home. That's all for part 1. I'll see you in part 2.